2010, quiz number 2, problem 2, bit balancer. In an effort to monitor the obscurity level of their encoding techniques, a super-secret government agency has asked you to take over development of the bit balancer. The BB, as it's called in this agency, is a simple synchronous FSM with a single input and a single output, which is 1 if the input has been a 1 during exactly one of the last 2 clock cycles, i.e. if the last 2 inputs are either 0, 1 or 1, 0. So on startup, the bit balancer should behave as if it's received only zeros thus far. Your predecessor in this job was Chip Ahoy, who got a C in 6004. Chip struggled for hours and finally demonstrated a 5-state FSM that behaves according to the above specification. Unfortunately, the state transition diagram he left you is incomplete. In its initial state, A, this assumes that only zeros have been entered. Your first task is to complete Chip's diagram and make his finite state machine work. What are the appropriate values for the outstates of C and E? Okay, so we were told that the output should be a 1 if it's had a 1 and a 0 for the last 2 inputs, right? So starting in this initial state, A, we have 1, and then we have another 1 if we're going to C. So for C, this indicates that the last 2 inputs were 1. So we want the output to be 0. Now for state E, go like this, we had a 1 and then a 0. So for state E, the last 2 were 1 and then 0. So we want the output for state E to be a 1. So if we want to fill in the missing state transition diagram for state C in the above diagram, we see that there are arrows, there should be an arrow going out of state C for both of the possible inputs, right? We should have both cases covered. So right now, it seems like we've only got this 0 case covered, right? We only know what to do when the output is 0. So we need to determine where it should go when the output is a 1. So we said that state C corresponds to the last 2 inputs being 1. So if the last 2 inputs were 1, 1, we're in state C, right? And then we get another 1. Well, then the last 2 inputs were still 1, so we should stay in state C. So we'll fill in this and put a 1 right there. Now, on part C, we're given an incomplete truth table for this finite state machine, shown to the left. So if we want to try and determine which state is which, we can start off by looking at the fact that in state 0, 0, 0, the input is a 0, and then we stay in state 0, 0, 0. So that must be state A because we have this arrow right here. So this is 0, 0, 0. Okay? Now, so if 0, 0, 0, so that's state A, has a 1 on the input, then it goes to state 1, 0, 0. So a 1 from state A. So this one, state B, must be 1, 0, 0. Now, if we're in state 1, 0, 0, and our input is a 0, then we go to state 0, 0, 1. So E is 0, 0, 1. State 0, 0, 1, input is a 0. We should go back to for state 0, 0, 1, input's a 0, we should be going back to state A, so that's 0, 0, 0, and our output is a 0 in that state. Okay, so if 0, 0, 1, we receive a 1 instead, then we're going to go to D, so 001 receives a 1. It should go to state D, which we don't know the bits for yet, so we're going to hold off on that. But we can determine by saying state D, we know when it receives a 0, it's going to go to, quote, 001, right? So, this one, when it receives a 0, goes to 001. So this must be state D. So this must be 010. So here, this must be 010, because when E is 001, it goes to 010, which is state D, and the output is 1. Okay, so now I think we have some information to answer part C. It says, what are the 3-bit state assignments for state B and for state D? So for state B, we determined that was 1, 0, 0. And for state D, we determined that was 0, 1, 0. And it also says, what are the missing next state values for the state encoded as 0, 0, 1? So that would be state E. And we just figured those out right here. So the next state from 0, 0, 1 when the input is 0 is this one right here. So that's 0, 0, 0. And when it's 1, that's this line, so it's 0, 1, 0. And we're done.